while we are still waiting, maybe I can take this opportunity to introduce the speaker to you. So today, we are very glad to have Dr. Patrick Groeneveld with us. So Patrick is a senior fellow at AMD and adjunct lecturer in Stanford, Department of EE. Patrick has a really extensive career in EDA. He had been with Cadence before, with Synopsys before, and he also served as chief technologies at Magma, design automation. And he contributed to the development of a RTL to GDS2 synthesis tool many years ago. And Patrick also worked with AI hardware startup and have a full professorship in electrical engineering in Eindhoven University. He's the finance chair of the executive committee of DAC. So you are still, right?
I'm still the finance chair of DAC, yeah.
Many years.
Yeah.
Yes, and Patrick earned his MSc and PhD degree from the Delft University of Technology in Netherlands. So let's welcome our speaker.
Thank you. It's a great pleasure to be back here. I was here in 2019, and it's great to be here in Hong Kong. I'm always love to visit this city. As Evangeline just said, I'm from Delft. This is actually a painting of the city of Delft, but it's a painting from 1660. And it was painted by the famous Dutch painter Johannes Vermeer, who lived in Delft. Delft University Technology is actually on this side of the river. It was built a little bit later, 1842. That's where I studied. And the old city here is very old. And actually last week I was in Delft. And you can actually recognize this church over here, which was built in 1350. And that's what we call the old church. And then the new church is from this was finished in 1490. So from before that Columbus discovered America. It's a very nice town and very picturesque. And I'm showing this as an intro because I want to talk about two people who lived in Delft. First is the painter Johannes Vermeer, who actually painted this painting, and the other one is the scientist Antonie van Leeuwenhoek, who discovered the microscope. And why I'm bringing this as a topic here, I will become a little bit clearer later, I hope. Yeah. So first, Johannes Vermeer. His most famous painting is the girl with the pearl earring, but he was an extremely good observer of light, and he managed to paint the light exactly as he wanted. Here's, for instance, another painting of him that shows him in his studio, and you see that the light coming from this side, and there's some cracks here in the painting, and he exactly managed to capture that. And also there's some serene beauty and balance in this painting that has not been surpassed before. And also, if you look what he did here, he sometimes used very thin paint here to put the water in, and therefore you get some very tranquil picture. But at the same time, to make it exciting, he put a dark cloud over there to make this part of the city in the shadow, and then put the other part of the city in the light, so you get a little bit of tension here. So he observed that very well, and and therefore made it work. However, he was a painter and not very clever with money. So when he died died deeply in debt. And this painting, he didn't manage to sell it. And the person then who helped his widow to sell it, to pay off the debt, was actually Antonie van Leeuwenhoek, who was a well-off cloth trader. And he had lived a long and happy life. They were both born at the same time. And in his spare time, he was a scientist. And he was the first one to develop a microscope and therefore look at individual cells. So the microscope was here developed in Delft. And I'll come back to that later. That microscope looks very primitive over there, but he was the first one to observe this. So the topic, what I would like to talk about, is to take you on a journey of what happened from the very beginning of design automation and from the very beginning of Moore's law, which is in the middle of 1964, to the current day. And if you see the influence of electronics that we had there, the electronics that put a man on the moon was actually, they were small gates. I mean, what was integrated was just 4 or 6 transistors on the chip, and that was performing an AND or an OR gate. And that's what made a simple processor that managed to put us on the gate. The first microprocessor from Intel was the Intel 4004, 1972. Then in the 1980s, we had the first personal computer. Then in the 1990s, the first mobile phone. In the 2000s, the smartphone. And now we have AI hardware. Every one of those is a very big driver for the consummation of electronics. At the same time, none of these technologies was possible thanks to what happens in the integration density that you currently could get in electronics. Even for smartphones like this, because you use digital spectrum and the digital signal processing that was required, you can only get it if you have a certain degree of integration with your design. So I'd like to explore with you what happens if we have this increase with Moore's law. At the same time, the Design Automation Conference, from which I've been involved with for quite a while, started in 1964 as well. And I also started in 1964. There's a picture of me. So there's a lot of parallels here. This year's DAC will be in Long Beach, and my first DAC was somewhere here. So yeah, that will be. But what I will try to show you later is important statistics. I mean, first of all, there's the Moore's law statistic. What happens when you get exponentially more transistors on the chip, and what are we doing with it? And I'll try to combine that with another few statistics and make these numbers come alive and a little bit give you some inspiration on what have we done within microelectronics to make things work. Okay, so to put things in perspective, this is a map of the United States. That's where I live, Silicon Valley over there. And now imagine that I'm looking at the chip and I think that the width of a wire, how about if that's the same as the width of a road? 2-lane road is about 10 meters wide. Yeah. The width of a wire on a 3 nanometer chip is 24 nanometer. Yeah. So if you multiply that out, that's a factor of 435 million. So imagine now you have a chip the size of your thumb and you increase it by a factor of 435 million. How large is that chip at that scale? Well, that chip covers the entire United States. Yeah. So now imagine we have roads shoulder to shoulder, not 1 layer, but 10 layers high. There's electrons driving on these roads. There's never any collision there because we design it optimally and we make sure it's correct. But another way, that analogy is very interesting because what we build here, these structures, whatever communicates a lot together, you want to place it close together because that's less transport complexity. So that comparison is very valid. And also the complexity comparison is very valid. Yeah, in the United States, we have 310 million people, or maybe it's more. 260 million cars and 140 million homes. If I compare that on this chip, the latest iPhone chip, that's this one, we have, at that scale, we would have 8 million miles of wire, and the US only has 2.7 million miles because it's only 1 layer. Yeah, so the scale, what happens on this chip is much larger. Also, if you multiply out the energy consumption of the United States, which is about 400 gigawatts on a normal day, that would only be 2 gigawatts if you multiply that. So we're doing some big magic here. We cram a lot of stuff and a lot of knowledge on a very, very small scale. And I think that's really important to realize that. On the same scale for Asia, if I would drop the same chip here at Asia, it would cover both India and China, so the half of the world's population will be covered by this chip. Yeah, but there's still many more transistors on this chip than there are people covered by this chip. So that scale does not stop to be I'm not stopping to be in awe by this scale. And I wasn't when I was your age. That already seemed very big a chip, but now it's beyond comprehension big. And I want to share with you what it means if the chip gets at this scale and what we do. If I zoom in on this chip, this is just there's companies who open up these iPhone chips and they take pictures of them. And then with the naked eye, you can recognize some structures here. Yeah. So if you look carefully, I can see, for instance, these blocks over here. They're probably designed as one block. There's a standard cells and all these little areas around it. They are memory macros. Yeah. So and then there's another block over here and another block over here. So this is probably how it was programmed. We know from Apple that they say, okay, they have 2 high-performance CPUs, 4 low-performance CPUs. Can anybody see them here? Let me help you. These are the 2 high-performance CPUs. Yeah, this is the cache related to that 2 performance CPUs. And then there's 4 low-performance CPU. 1, 2, 3, 4. You can see and there's some shared cache over here. And then there's the level 3 cache over here. And this is the NPU, so that's the inference hardware for the AI inference. And that inference hardware is actually relatively small, to my surprise. Yeah? So kind of, now it's, let's say 60% of the chip is what's processing. This is the GPU. And not that clear, but there's also some repetition, and all the other parts are sort of blocks that do acceleration. But it's always interesting to see how this evolves. Yeah. Then let's say the end of Moore's law has been predicted many times. Yeah, I remember when I was your age, you say, "Oh, it's going to stop very, very quickly." Yeah, and if you look here, they say the shrinking will stop. And yesterday at the conference, we heard from Professor Hu. He said he came up with the idea, how about to make FinFET? And then suddenly we could still make it smaller. So every time we do get over this boundary, because if you look at this article that predict when Moore's law was dead, they predicted it was dead in 1997. They predicted it was dead in 2016. I think before I retire, it will not be dead. Yeah. And the biggest proof of that is we could just look at what chips are in our smartphones. Yeah. And the simplest thing is just to look at the cadence at which Apple makes its chips. Yeah. So here I plotted the iPhone 4 all up to the last iPhone. Last iPhone, and the last one I forgot to put here, iPhone 16. Yeah, and you can look up online how these chips look like, and we also know the process node and the size. The size doesn't change that much over time. It's always about a square centimeter. But the technology, of course, improves, so that's what crams more chips on it. And if I take that first iPhone, or not the first iPhone, the iPhone 4, the big one, 45 nanometer Samsung process, and then I go to the next generation, next, and keep on scaling. 2015, 16, 17, 18, 19, 20, 1, 22. In the end, how much did I scale? 100 times. So now that chip has 100 times more transistors than that earlier iPhone. Yeah, 100 times. That's a lot of more hardware. Yeah? And normally you don't get that easily 100 times. Yeah. So in Moore's law, you would expect doubling every 24 months. That means expect 42% annually. What I get is 36% annually increase in transistors on this chip. So Moore's law seems to be alive. It's not perfect, but it is increasing. Yeah? And it's consistently increasing. We put more on it. And the other interesting comparison with that 100x is say, hey, let's compare to something else. For instance, with cars. Yeah, and here if I look from 2010, this was the latest data I could find, 2010 and 2023. Here the car fuel economy, and here the car horsepower. It's about 20% better. Yeah, the fuel economy got 20% better, and the horsepower got increased by 20% since 2010. Unfortunately, some of that gain is negated because the cars also start getting bigger. So you get kind of, we like our big SUVs, so some of the efficiency is eaten back. But at the same time, when we get 1.2x here, we got 100x more material to work with. This one, 100x. So 100x, yeah. There's one more law that is associated with that 100x. And can you guess what this law would be? Any idea. So this is the exponential curve that we get from Moore's law. Yeah, more and more transistors. What Moore's law would be associated with that? Any guesses? What would Lass's law be?
The transistor count is multiplied 100 times, but the performance is not.
You're very good. So basically what the law says is the perceived usefulness of this product is an underlying technology's logarithmic function. So you have to put exponentially more transistors in it to make you a little bit happier to buy the next generation phone. Yeah, so the usefulness went up and not by that much. I owned this iPhone 4. It could do FaceTime. I could browse the internet. I could do my banking. I could phone with it. I could take pictures with it. It is really nothing that phone could not do that my current phone can. Yeah, maybe a few things, but it has 100 more times transistors on it. Yeah, of course it's smoother, it's a little bit better, but it's not that spectacularly better. Yeah, so but this is a great law for us in this business because it means you consume all these transistors. You still want all of this. Yeah, so it's an interesting observation, and no other technology you can afford to do that because you don't get 100x in the automobile world or in the airplane world. Airplanes didn't get any faster since the 1950s. Yeah, so now we get these more transistors. Let's look what happens when we put, what are we gonna do with these transistors? This is the iPhone from 2012, and I took that just because it looked, and let's look at the iPhone from 6 years later. Yeah, so the 2012, the iPhone was about half the GPU, about a quarter was 2 CPUs, and then some assorted other blocks. In the total, about 15 different blocks on this design, on the system on chip. If we look at 6 years later, 10 times the number of transistors in this case, you see a lot more blocks. I manually looked here and then put little boxes around it, but I think what the floor plan was that Apple used. You see that kind of in this case, about less than half of the chip is still the processing, and all the half is video encoders and decoders and secure enclave and whatever other stuff you hardened on it. And of course, you do that because whatever you implement as gates on this chip consumes a lot less power than if you would do the same operation on a general purpose CPU or even on the GPU. Typically, you can say that if you do something on the CPU, compared to doing it in this one, is a factor 1,000 in energy efficiency. Yeah, so if you care about your memory usage or your battery usage, you want to harden this in blocks. And if you're a large company like Apple, you can afford to do that and not have to do it in software. So it's interesting to see what happens. So we can make all kinds of specialized blocks and make them do exactly from certain operations that we know we need with the least amount of power. Then it's interesting to follow, what happens now within recent generations. So here I looked at the iPhone 11, 12, 13, 14, 15, 16, and you see the floor plan didn't really change that much. Yeah, so they picked a floor plan, they pick a design, and then they stuck with it. And now if you look at nature, a similar thing will happen. If you look at all the mammals in nature, we have about a similar floor plan. A brain over here, a heart, lungs, the ratio and where they are placed. It didn't change that much. Yeah? So you kind of make incremental operations of, even though these chips got a lot better. And compared here the last two iPhones, this is the latest iPhone before, you see the floor plan is almost exactly the same, and this high-performance CPU is almost exactly the same to me, at least from the outside as the other one. However, according to Geekbench benchmarks, this one is still 15% faster than the one over there. And partially, that's of course because it's probably better technology in 3 nanometer or more evolved 3 nanometer technology. But you see, they didn't radically change the design. And it's also because floor planning at this level turns out to be a very hard problem, not that easily to solve. If you start mixing this around, likely you're going to get something that's much worse. Yeah. So interesting to follow that. So here I put the key chips that we've seen in the last 60 years. over here, starting with the first integrated, it's a 16-bit SRAM from IBM. Some important processors here, the 8086, the very first one. It had, what is it, a few 100,000 transistors. Motorola 68,000 had 68,000 transistors, very famously. That's what it was called. That was the chip that went into the first Apple Macintosh. And then we go up, and if we go until today, we're seeing that smartphone chips have around 16 to 20 billion transistors today. Our largest Xilinx FPGAs have 100 billion transistors. Yeah. And now the latest NVIDIA sync are pushing 200. I didn't put it on this one yet. If you want to get really big, this is the Cerebras wafer scale chip. That's 2.4 trillion transistors on the chip. But that chip is the size of a dinner plate. Here you see it. Or you go vertical, like what happens in all the flash memory. There we have many, many layers. And then also with 2 terabyte micro NAND flash memory has 232 layers. Yeah, so you either go vertical or you go horizontal to get to extreme numbers of transistors. I mean, we're talking trillions of transistors. Okay, so that scale of trillions of transistors, just to put it in perspective, I mean, what's a trillion transistors? Yeah, if you look outside in the sky on a clear and dark night, you're able to see 10,000 stars in the sky. We have about 7 billion people on Earth. We have more transistors on most chips now than we have people on Earth. Yeah, the number of neurons in our brain is 80 billion. There are chips now that have more transistors than neurons in your brain. Yeah, so we're really talking mind-boggling scales. At the same time, the importance or the economic importance of semiconductors has increased a lot. This is just in dollar amount. Last year, it's almost $800 billion worth of semiconductor sales. Then we're talking everything together, NVIDIA, TSMC, the whole thing. 700 billion. More interesting is actually to see what's the influence of microelectronics or tech on the market. On the US stock exchange now, half of the market cap, half of the value is based on tech. And we include companies like Uber, but also, of course, NVIDIA. And that has never been as high, because if you go back in 1964, it was maybe 6%. Yeah, so electronics is from insignificant is now the most significant technology that we have in the world. Interesting here, you guys probably were barely born here, but there was a dot-com boom. There was a certain moment when we were so excited that you could do online shopping. And that caused a tremendous boom. And then we suddenly had 40% of the market was in tech and electronics. And then that crashed miserably in 2001. And now here we have another boom caused an AI boom, and we wonder whether that one's going to have a crash or going to go up. Yeah, so interesting things to consider. The other interesting thing, and that's a little bit bobo, is we're here in the automation business. Yeah. So are we causing unemployment by automating this? Yeah. Here I took the US unemployment rate. Yeah. So and there's the recessions are over here. Yeah. This is dot-com crash, the subprime mortgage crisis, or of course COVID, which got us a big peak, and now we kind of lower. This is the US unemployment. I don't know the numbers here in Hong Kong. So very interesting that the very first design automation conference, the very first presentation at the very first design automation conference was called Economic and Social Aspects of Automation. It was called Design Automation Conference. It was not specific for electronic. It was just what happens if we start automating jobs? Do we take people's livelihood away? And this is a guy from the US Department of Labor who gave a presentation and said, well, if it doesn't happen fast enough, it will probably not have an influence if we just educate people and let them migrate to jobs, to a little bit more higher skilled jobs. And that has largely been true, because if you look in 1964, the unemployment rate was slightly over 5%. And now the US is kind of 4.5%. So likely we didn't kill that many jobs. Yeah. However, there's some people specialized in this. This is an economics professor at MIT who wrote this an interesting paper, said, why the heck do we still have so many jobs? Because automation should have taken away these jobs. And he said, well, what we've taken away are mainly the routine jobs. And at the same time, we created new industries. Yeah, there's whole new industries that are enabled because of that. So if the workplace, if people get educated for the right jobs, we have more high-skilled service jobs available now. Things will be okay. This was before the dawn of the impact of AI, and now the big question is, what does AI do for us here? Yeah, will we see a productivity boost, and then everybody gets more productive, and they get even more economic activity, and everything will be fine, or do we rob people of their jobs? Yeah, because he's told everybody to start becoming a programmer, and suddenly, ChatGPT can do programming much better than you can. So there's a big misalignment here. It's interesting to look a little bit more at this paper. I had a quick look there because it contains this graph, which at first I didn't fully understand, but it's actually very interesting. So this tells here the change in jobs in a 10-year period, if you're a low-skilled worker or if you're a very high-skilled worker. All of you are likely on this side of the graph over here, but let me help you a little bit in what this means here. And that kind of in the previous century, 40, 30 years ago, what indeed happened is that lower skilled jobs were automated away. Many factory jobs got automated away. And we got more higher skilled jobs, and that balanced things out. However, what we've seen in the past decades, it looks more like this, that we have still many lower skilled jobs, people who clean, people who serve you in restaurants, because we kind of automated away most of the things you can do at factory, and slowly, and especially with AI, it comes for the middle skilled jobs. Yeah, people who write advertising or write little letters that ChatGPT now can also write. So you have fewer middle, and only at the very top you're still a little bit safe. Yeah, and the question is, of course, if this AI, whether it will cause even less unemployment in the middle. Yeah, and if that happens, of course, we'll get more inequality, and that might have some impact. But okay, it's a bit above our pale scale to completely follow this, but it's something to think about. AI, of course, will undermine the scarcity value of what you did. I mean, I spent decades of my career writing C++, and I feel mildly frustrated now that I can ask a tool and it does a better job than me. Even though I still like the challenge of programming, it's just like playing chess. You have to to resign to the fact that the machine can do this much better than you, and in the end. Yeah. So that unique skill that I have is not unique anymore because the machine ate it away. Okay, so it's clear now that where we are, and that we kind of now have the whole reason why you've heard of NVIDIA now, the largest company in the world. This is a chip company, our business, largest company in the world, because with the computational demand for AI processing is through the roof. Yeah. So, and that is because these LLMs need tremendous amount of relatively stupid computation. Yeah, it's basically multiply add, and we optimize it, but it's about getting the right structures there and doing this. But it means still that we need boatloads of silicon, and it's really important to do it efficiently, low power, everything. So that is a thing that we do. Then it was always a question, well, will it be CMOS, or do we do optical or carbon nanotube? No, it will be CMOS, yeah, because that's what we know how to do. And all these fancy technologies likely will not get us anywhere. So it's all a long introduction to say, hey, we're here in the business of electronic design automation. Yeah. So the idea is to go from a block diagram or a higher level description of a design. In this case, it's a RISC-V processor. And at the end of the flow, I expect a placed and routed design. And here's kind of interesting that how does it actually physically start to look like? Boatloads of standard cells and a few memory blocks on the side. And if you look closely, this is the instruction cache. That's a piece of memory over here. But the ALU becomes this blob over here, floating point unit, is a lot bigger. So, and all of that merging together, but the interesting observation is that this is built from standard cells. So what the square block here is not a square block here anymore. We took away that logical hierarchy that we had, and we blasted it away because physically we like it like this. And there's a good reason for it. That's a point I want to make here. That standard cells, the standard cell methodology is actually the reason why we can make chips. Yeah, you don't want big blocks because we don't know how to place them well. So very well established. We have a very nice set of abstraction levels that we go through when you do electronic design information. You go from C++ or TensorFlow, do architectural synthesis, high-level synthesis, logic synthesis, physical synthesis, place them out, and then you end up with masks. Most of this flow you can do now with a push of a button. And that is because we have decades of your predecessors coming up with algorithms, and we tune it together, and companies like Cadence and Synopsys and what I work on at AMD, we stitch it together and we make a product that runs through that as well. What we expect now when AI enters this flow is that you first have this AI-driven loop here, that if you run through the flow and the result is not that great, it will analyze the result, it will automatically start mucking with making some changes and changing some parameters and running it again. And that way you don't have to do this manually anymore. We can, and actually what I do a lot, I vibe code a lot of RTL. So I can just ask ChatGPT to write me, well, make a multiplier that does this and connect it to that. And the outcome's pretty decent RTL code that I can run in this flow. I vibe code a lot of scripts, yeah, to hack it all together. It's getting remarkably good at this. I code whatever C++ code that is there. Of course, I do is VS Code and do a lot of prompt-driven C++ development now. Also because the complexity of the system as we have it in AMD now, our tool has 120 million lines of code. So if you step in the middle of there, you have no idea how that, I mean, it's very hard to comprehend it. And the AI helps you a lot with that comprehension and helps you not making stupid mistakes. And we expect from you guys some AI-driven algorithms to make this flow better. Yeah, and lots and lots of publications are on this one. So to get the bigger picture of this, I think it's kind of interesting to see. So here we have this flow from system, RTL, circuit, mask. If you go below that, it goes to fab. Then we package it, put it on the circuit board, we assemble it in hardware, and then it's a product you can buy in the store. Yeah, and above there we have some embedded software, some architectural synthesis, and that will be kind of your entire tool flow over here. And if you look at the set of companies that serve this ecosystem, we have Cadence, Synopsys, and Siemens EDA is the market leader, which kind of gets you from here to here. About $14 billion per year worth of business there. Below that, you have the semiconductor equipment company guys like ASML, Applied Materials. That's about $20 billion a year worth of business. Then we have the PCB printed circuit board business. That's a little bit less. It's $5 billion a year. And then you have factory automation equipment. So kind of the whole tooling chain that you have there. And on top of that, you have PyTorch and CUDA as tools to do it, or you have IP like ARM or RISC-V that you toss in the top in this flow. So that's kind of the ecosystem that you have there. And if you look at the semiconductor components that you get from that, we have, of course, the fabless semiconductors, which again, NVIDIA, the big one, Qualcomm, Broadcom, AMD, we're fabless as well. And then whatever goes there feeds into mainly TSMC, that's 70% of the market, Samsung Global Foundries. Or you have the integrated design manufacturers, Intel, Samsung, TI, the analog guys. They own both the fab and they design the chips. And below that, you have the printed circuit board companies. That's a whole world by itself. And you have, of course, contract manufacturing like Foxconn, who are actually building the iPhones that you buy in the store. And then, if you think it's, well, who are the customers from that? And these kind of vertically integrated companies like Apple, Huawei, Amazon, they actually make these products, and they generally design their own chips. So they are customers of us for these pieces of flow. And then at the bottom, they do contract manufacturing. And then we have a software industry and a hardware industry like Dell. And so it's kind of the whole world sticks together, and we see this kind of, I put us here in the middle, but we are an essential part of this flow, yeah. And we're talking $800 billion in electronics, whereas of course these system companies are much larger. So why are we successful? So why are we good at this? It's kind of interesting to compare chip design, so electronic design automation, to mechanical design. Yeah. We have many more components that we design at the push of a button. An airplane only has a few million parts. Yeah. But it costs a chip design, I mean, a high-end chip design costs maybe $50 to $100 million to design a large SoC. But to design an airplane costs $20 billion now. Yeah. And why can't they? Because the airplane looks the same as 50 years ago. Yeah. Two wings, engines on it. Why is it so hard to generate that airplane? Yeah. And the reason for that is that we have this magic standard cell. Yeah. This standard component that we use everywhere. And that makes it possible to have an automated flow, which those guys for some reason don't have. Yeah. And I'll come to that in more detail. So let's look at the standard cell. Yeah. There's enormous beauty in this abstraction level of the standard cell. This is the logic symbol. This is the electric contents of an inverter. And this would be the layout of an inverter. Yeah. Two transistors, the N and the P on top of each other, and two power rails at the bottom. So we have a whole library of those. Inverter, this is my NAND 2, NOR 2, NAND 3, and you get a little bit larger. This is my flip-flop. Yeah, typically flip-flop are the largest components in the standard cell library. But the important thing of the standard cell is that these rails, they make sure that you can place them anywhere. You don't have to think about it, and all the complexity is hidden in that thing. I buy this standard cell from another company and I just use it, and I get just a file, say how fast it is under which conditions. So this is a very powerful abstraction level that works very well with the algorithms that we have. So what do we do with these standard cells? This was a placement that I generated a while ago, and every one of these little green boxes is a standard cell. Some are a little bit wider than others. I mean, the white ones are flip-flops, and the smaller ones, they are NANDs or inverters, or sometimes higher drive density inverters. Here there's a lot of small ones, and there's sometimes big ones. So, but the overall, though, their size variation is limited, and that is really key towards a successful flow, because we have a successful placement as a result. After I place them, I can route them. And of course, you want to place them in such a way that you can route them. You want to place it just close together that the router just finishes. Otherwise, if you place it too far apart, you have too long wires. So it's really important to tune it exactly right. Yeah, not too close, not too far, not too close. And then, but the key technology that we have is placement. And here is from one of Andrew Kahn's group, and this is one of the things that you can get online just from GitHub. And every one of these red dots here is a standard cell. And because they can be considered little dots, you can model their attractiveness, and they're attracted to each other if they're connected to each other, and at the same time they will be attracted to empty space where they can get. And if you tune that properly, you place them and you get a very good placement, and you can do that for millions of standard cells in one shot. Yeah, and this methodology works. Why does it work? Because it's nicely integratable. This is what typically is some form of quadratic placement, and the derivative of quadratic function is linear. There's no bumps in there, so it ends up very smoothly. That's why this methodology is very, very nice. Yeah, and that's the reason why things work. You saw on all the chips, half of the area is these standard cells that are placed with these methodologies. But then they're placed between larger macros, and if you have larger blocks like this, then is where trouble starts. Because placing those blue blocks here, we haven't solved that problem properly in 60 years of electronic design automation. The blocks vary in sizes a lot, it's really hard to come up with the optimal placement, and it's typically a very manual process that you do. Because imagine that you do make one mistake, you shave these things too close together, then all these blocks can't be placed here, they have to be squeezed over there, and that will be a very suboptimal placement. So it's really important that the macros are placed in the right way. And our solution to that is, if we can't place the macros, let's make sure we have as little as possible of those. Yeah, so we're going to have as few as possible big macros that we have to place, and we're going to place as many as possible things in standard cells. That's the methodology that works. And that resulted then in this 3-level hierarchy. First of all, we have a standard cell, and that's where we hide all the magic of the physics and all the complexity there. Then we put a lot of standard cells together, maybe 10 million of them. We make a block. But all the wires are homogeneous, all the standard cells are about the same, and that's why this methodology works. And then we stick that together and we make a chip, and then we get different size of blocks, and then where the trouble starts, because this is a hard process. Apple has a whole team that's busy solving this puzzle and trying to tune that properly. We have some tools to help us with that. We saw some papers to do this with reinforcement learning that has been fairly unconvincing that it's actually a methodology that works. Yeah, so all of that, let's go back now to the 17th century. To the standard cell that was discovered by Anthony van Leeuwenhoek. So he was looking through his microscope to everything. He picked a drop of rainwater and discovered, hey, there's little animals flying around there, yeah? And it turns out to be microbes there. He took some saliva out of his mouth and said, hey, there's all kinds of stuff living in there, yeah? What the heck is that, yeah? Or he took some blood. He said, it was the first time to say, hey, what is going on here? Took a little bit of the tree and said, hey, there's a structure there. So he said, hey, nature builds his stuff from cells, yeah? And and if you look at the history of nature, yeah, 4.5 billion years ago, Earth was formed. And then relatively shortly afterwards, so 3.8 billion years ago, the first life popped up on Earth. There were primitive cells, but they couldn't reproduce. And it took life until 1.8 billion years ago to come up with the modern cell. That is a nucleus, a mitochondria, and so there's a lot of complexity built into this single cell, but it's still a tiny little thing. But so you see, it took a long time to develop this, and then we had this cell, and then it took until 541 billion years ago, and suddenly nature discovered composability. Say, if I put these cells together, I can make an organism that's even more successful. And suddenly you have an explosion of little animals and plants coming up because we figured out, hey, I can arrange these cells together and specialize these cells a little bit and make an organism out of this. Yeah, very similar. It turned out to be very similar to the way that we make chips. Yeah, so let's look at these cells then. Yeah, so this is a standard cell, a lot of components. I mean, a standard cell from nature, a lot of components. Our standard cell has a little bit fewer components. Yeah, we have transistors, some diffusion tiles, and some metal wires. But I mean, it's not nearly as complex as what nature came up with, but it's still important that all the complexity gets hidden in this little box. And then we can put these boxes together, and then suddenly I make a successful organism. Yeah, similar what we will do here. The scale is not the same. Yeah, our current standard cells that we put on the chip are at the same scale, would be this size over here. So, and biological cell is 100 to 200 times larger than the standard cell that we put on the chip. But it uses about 10,000 times less energy. Cells are really, really efficient, but it may be not fair because each of these standard cells, they might switch with 2 gigahertz. Yeah, whereas biology doesn't switch gigahertz, it's switching in hertz. Yeah, so it's not but still the anatomical similarities are really, really surprising. Yeah, because if you look at the human body, we have 78 organs in our body. Yeah, all built from standard cells. If you see how many different cell types we have in our body, it's about 200. How many cell types do we use to make a chip? In the order of a few hundred as well. Yeah, so it's not that dissimilar. Yeah, how many blocks do we have here? How many organs? Maybe 75, 100 blocks. Yeah, on the chip. So how much power do we use, each of us in the room? We are about 400 watts of each of us power. A typical chip is also 400 watts. Maybe it's this coincidence, but I think it's an interesting thing to consider. So here we have this 3-level hierarchy that we see on the chip. Yeah, standard cells, put it in a box, place the box here, put lots of them together. That's my chip. Here I have standard cells in the body, put it in an organ, put them together. I have an organism. Similar 3-level hierarchy that nature came up with and that we came up with so it's kind of interesting to follow that comparison. I put some here. Of course, our body, we have 37 trillion cells in our body, which is a lot, yeah. And blue whales have even many more cells. So we don't have that complexity yet on the chip. But other things are fairly similar. Of course, they're built in a different way. For instance, all organisms have infrastructure to distribute energy. Yeah, in our case, it's the blood circulation that distributes. And on the chip, we have a power wires for that. We have clock network and neural network. We have nerves in the biological system. Interesting thing is that the cells in our body live for about 8 years. And we live, if we're lucky, about 80 years. Yeah. So whereas these standard cells, economic lifetime, after every 3 years, we toss them away. But if we want, they probably live for 10 years. Yeah. So the biological still wins over there. Of course, there's a lot of error resistance and resilience in biological systems. Yeah, we can heal ourselves. That's almost none in circuits that we build. Yeah, if it's broken, it's broken. We can't do much. Disposal 100% recyclable. Of course, here and electronics are not recyclable. Yeah. So interesting, but I think the similarities are much bigger than actually what we should give it credit for. Yeah, because cells are similar size with minor variations in types. Our methodology that's successful did have requires that we can only place this much transistors if we put them with standard cells because it's differentiable. We use uniform plumbing, a simple plumbing system to make sure that the energy gets supplied for that. And composability into IP blocks, building many of these equals, and somehow, if we put it a lot, intelligence occurs. And I think now we have getting to a scale where we get Miss Moore's law. I think intelligence, machine learning, artificial intelligence was about to happen, yeah, at this scale that we have there. Yeah, and it happened in nature when you put the stuff together, and it likely happened here as well. So just to make that to go with that intelligence theme, yeah. This is the cortex of a rat. And here it was you see that they identify several layers. So that's very similar to the neuromorphic deep learning network that we have. We also have an input plane that feeds into another plane, that feeds in another plane, that feeds in another plane. So these layers are likely operating in the same way. We don't really know how the brain works, to be frank, yeah, but this is our best guess from what we see and what we can observe. Our good friend Lou Scheffer, you know him well. He worked for a while, or until recently, he worked for Howard Duke's labs to try to dissect and use EDA methods to figure out what is the structure of the brain, and can we use EDA methods to unravel that structure. Yeah. So and then if you think, okay, when does intelligence occur? So what I put here vertically, logarithmically, number of neurons in the brain of the animal. Yeah, so this is just 100, and the smallest worm only has over 100 neurons, and it can reproduce, it can squiggle, it can do with very few neurons. Then we have rats, which already have billion neurons in their brain. Crow is very interesting, very intelligent bird. Crow has as many neurons as a cow. Interesting, yeah. That's just because a cow isn't that keen on optimizing for lightweight. Yeah, a bird needs to optimize for lightweight and intelligence, and it did that for a long time, and a cow didn't. Dogs are slightly more intelligent than cats, or seem to have more brain power. Remarkable is that dolphins actually have bigger brains or more neurons than chimpanzees have, and we are at about 80 billion. Yeah. What that's only part of the picture, of course, because that's the amount of cells and neural cells. But every cell we're using synapses connects to 1,000 other cells in our brain. And the strengths of these synapses encode memory and encode intelligence. Yeah. So if I multiply that out, we have about 100 trillion weights in our brain, whereas LLMs like ChatGPT have about 3 trillion weights in our brain. So we have still a tremendous amount of overpower in our brain compared to what ChatGPT has. But so that's an interesting comparison to make here. Okay, so LLM versus human. So now if you see, hey, because now coming back to this theme, like when does intelligence occur? I can more or less say that simple animals and also the first chips that we made, they did simple finite state machines, yeah, and that's also how simple animals operate. But if you go higher and higher, you get higher levels of intelligence, yeah, and intelligence that you could say is what you get with machine learning is probably, yeah, the level of intelligence that you can get from a cat, and that's we're now probably reaching the scale where artificial intelligence and real intelligence and artificial intelligence will cross, and it's to be expected that we get something that behaves like an intelligence. One more point to make here on this scale. This is Half Moon Bay Beach in California, close where I live. It's my favorite beach. Nice sandy. Ocean is going. It's always often like weather here to hold the hand of sand. That's about 10,000 grains of sand. That's about as many stars as you can see with the naked eye. And then I had a philosophical thought, and that philosophical thought was given in many ways as well before, like what are large numbers? Yeah, in the Bible, 3,000 years ago, it was written. They say your descendants will be as numerous as stars in the sky, or as sand on the seashore. Yeah, so two, what you think is really big numbers. Yeah, so let's see how big these numbers are, and how does it relate to the number of transistors? Yeah, because Carl Sagan, it was a famous science educator, he said, hey, there's more stars in the universe than there are grains of sand on all of the beaches of the earth. I want to check that, whether that statement is true. Let's figure it out. Or you can say now, are there more transistors on earth than grains of sand on all the beaches of the earth? Let's figure that one out, yeah? It's interesting. But before to do that, yeah, when I was walking here on the beach, I sort of came to another thought here, because if you look here on the beach, the waves come in, and when they recede, you get this shiny layer of water. I don't know whether you've walked that. And then if you step on that, you see here that layer of the shiny layer of water. If I step on it, actually the shininess disappears at the point where you step, around where you step on the sand. Have you noticed that? Yeah, so there's this thin layer of water over here, and you step on it, and around your feet, the water disappears. And that's kind of counterintuitive. Normally you would step on it, you say, hey, the water should ooze out, and you get more water there. Any idea why that's the case? Why would stepping on sand make water disappear rather than getting more water out? It's not. It's not even that counterintuitive. But think of it: if the waves deposit these grains of sand, they're not in a fairly optimal way. At the moment when you step on it, you disturb the structure, and you create space between the grains of sand, and the water sinks away. And the interesting thing is that's exactly how MOS transistors work, right? Because then, rather than a physical force, you put an electrical force there. You disturb the structure, and either you make it conduct or you make it not conduct in a semiconductor. So sand is therefore, or at least sand on the beach is a nice, let's say parable for MOS transistors. Yeah, it's very similar. Another thing you can think is, hey, so let's see, more sand or stars, which is greater? Yeah, so if I take the average grain of sand is about 0.5 millimeter, if I would cut it into half, you get 0.2 square millimeter. That's already enough to put 39 million transistors. Yeah, so it's still an interesting thought. But in my calculation here, I think there's about 6 to the power of 21 grains of sand on all of the beaches on Earth, and I did that by just calculating how many grains of sand are in a square meter, then approximating how wide is a beach, how deep is a beach, and then you can look up how many miles, kilometers of coastline on the Earth is actually sandy and versus how many is rocky. And you get roughly to important number 10 to the power of 21. Yeah, that's the total number of grains of sand on the Earth. The number of stars in the universe, the astronomers are not entirely clear, but if you look at their own Milky Way, it has between 100 billion and a trillion stars, and there's 100 billion and a trillion of Milky Ways in the entire galaxy. So you multiply that out, you get to something like 10 to the power of 22 and 10 to the power of 24. Let's pick the big number, 10 to the power of 24. So there's definitely more stars in the universe than grains of sand on all of the beaches in the Earth. Right? So how many transistors are alive? Well, I had to guess that, and you can basically look how many wafers does TSMC produce, and then multiply that, where there's about 3 trillion transistors per wafer, and they have about 40% of the market, and then multiply that by 0.4, and divided by 0.4. So I get to about something to the power of 19 million transistors, but we forgot about flash memory. A flash memory, which is now all the hard drives that we have, that's in the order of 10 to the power of 21 transistors that we need. And I reverse engineered that from the size of the market and about the average cost of a terabyte of flash memory. And you need about 1 bit cell, so one transistor, and the flash memory encodes 6 voltage levels, so it encodes 6 bits per cell. So if the average lifetime is about 3 years, I think the number of transistors is in the order of 6 to the power of 21. After I did this calculation, what is it, 1.5 years ago, and last week I asked ChatGPT, and it agreed with me. It was just roughly in this ballpark. So same amount of transistors on Earth as grains of sand on all of the beaches on Earth. Yeah, but we still have more stars in the universe than transistors. But maybe within our lifetime, we will surpass that. It's unbelievably large numbers. Yeah. So we have here a man-made structure that's bigger than, truly astronomical number. Yeah. Here, put it all together, logarithmic scale. So total number of stars in the universe, and this is kind of what we can put on a single chip. So interesting stuff. Weights in the LLM model I put there as well. So in conclusion, yeah, so an evolutionary Moore's law that gave us every year more transistors gives us suddenly new technologies. Yeah, we saw suddenly it gave us first cell phones, and it gave us smartphones, and now it gives us artificial intelligence. Literally astronomical number of transistors. Suddenly we can build stuff that's very similar to the way that nature has built things. This has profound impact on society, or impact of society, what we did in the past, we tried to hide from. Now we are truly shaping society by what we do here as an industry. And maybe it's sometimes a little bit time to start thinking about, is this all the right thing that we do? Yeah. The design methods that we have in EDA have slowly evolved over time. So we've been using synthesis place route as we have now the past 25 years. We're now integrating some AI methods, but in the bigger picture, it's still the abstraction levels we still hold the same one. Somehow we pull it off, yeah, even though every 2 years the number of the transistors double. Yeah, and the key how we pull it off is we have this composable standard cell at its core and how it works. And with that, I thank you very much for the attention, and I open the floor up for questions. Yeah.
Any question? So very interesting talk, and give us a vision, which is more global, bigger. So So, but at that time in the Bible, we don't have standard cell, so they only come out with sand and
That's right.
star.
Yeah.
So, okay, so if there's no question, actually, I wonder why you have so many pictures of the internals of the iPhone.
That's very easy. Just
Generation you have in the picture.
yeah, just put it in Google. Apple chip A14 dye photograph. It will pop up. It's very easy. Yeah. So, and then the rest you have just to look and start guessing. So, but I find it interesting because that's the only one where we can kind of follow generation after generation, and because it's the same application, you can kind of follow what's apparently back plastics. At the same time, Apple is the most secretive company in the world. We always at the ADA, we want to invite them to give a presentation on how they do things. They never ever share anything. So this is the only way in which we discover. And the industry is sometimes very secretive because even when I was at Synopsys, TSMC wouldn't share anything with us, even though we are the ones to supply with the timing sign-off and all the other tools. So we have to hire other companies to reverse engineer what they do to tell us how things work. Yeah. So it's, yeah. Yeah.
Okay, so any question you would like to ask? All right, then I think we just end the seminar here.
Okay, thank you.
And,
Yeah.
thanks. Let's thank the speaker.